Welcome to the next lecture on modulation techniques for mobile communications. The outline for today's talk is as follows. We will start with a brief recap of what we have learnt in the past few lectures, followed by the performance analysis of digital modulation techniques in slow, flat, fading channels. What we will learn today is that modulation techniques get adversely affected in fading channels as opposed to additive wide Gaussian noise channels. So, we must come up with some fading countermeasures so as to ensure that the existing modulation techniques still hold good for fading channels. We will then look at the performance of digital modulation techniques in frequency selective mobile channels. So, those which are using large bandwidth. In specific, we will look at the performance of pi by 4 DQPSK in fading channel with interference. Finally, we will take up some examples from bit error rate simulator called BER-SIM. First, the recap. We have looked at a series of linear digital modulation techniques. The prominent ones were binary phase shift keying or BPSK, differential phase shift keying or DPSK, followed by the quadrature phase shift keying or the popular QPSK. We then looked at the two versions or slight variations of QPSK called the offset QPSK and the pi by 4 QPSK. We then moved over to the domain of constant envelope modulation techniques. We studied the binary frequency shift keying and looked at the minimum shift keying as a special case of FSK, followed by the Gaussian minimum shift keying or GMSK, which is popularly used in GSM standards. We then talked about Emery PSK, followed by Emery QAM or quadrature amplitude modulation, where we play both with the amplitude and phase of the modulated signal. Finally, we looked at pseudo noise PN sequences and talked about certain spread spectrum techniques. The first one we studied was direct sequence spread spectrum technique called DSSS, followed by the frequency hopped spread spectrum technique or FHSS. Specifically, we looked at the performance of each one. So, this is what we have done so far, and today what we want to do is look at the performance of certain known digital modulation techniques in fading environments. What kind of fading environment? Both frequency flat and frequency selective channels. So, let us look at the introductory part. The mobile radio channel is affected by many factors such as fading, multipath and interference. In the earlier part of the course, we have seen how fading affects the received signal. Multipath fading is the most common cause of fading, and if the frequency bandwidth of the channel is not very large, we cannot resolve the various multipath components. On top of that, we sometimes work in multi-user scenario where we have interference. We then have observed that the performance of different modulation techniques in the additive wide Gaussian noise channels. Somehow we have found that most BPSK, QPSK, FSK kind of modulation techniques fall off exponentially with increasing signal to noise ratio. That is, the bit error rate goes down as we increase the SNR. So, bit error rate gives a good indication of the performance of a particular modulation scheme, but it does not provide enough information. The probability of error is another way of judging the effectiveness of a given signaling scheme in a mobile radio channel. Bit error rate and probability of error for many modulation schemes under various types of channel impairments can be evaluated either through analytical techniques or through simulations. Today we will look at both of them, the analytical method as well as through simulations. So, now let us look at the performance of digital modulation techniques in slow fading channels. Flat fading channels cause a multiplicative variation in the transmitted signal ST. If you look at the received signal here put in a box RT, it is a multiplicative factor which has both an amplitude variation and a phase variation times ST plus the noise NT. Since slow flat fading channels change much slower than the applied modulation, right, it can be assumed that the attenuation and phase shift of the signal is constant over at least one symbol interval. What does that mean? That over one signal interval we have this alpha t is a constant alpha and theta t is a constant theta. Therefore, the received signal RT may be expressed as follows. Here we have put alpha as a function of time and theta as a function of time. NT is the additive white Gaussian noise. So, please note the multiplicative factor coming out as a result of fading. In our previous lectures, we have seen why it is a multiplicative factor. Performance of digital modulation in slow flat fading channels. To evaluate the performance of error of any digital modulation scheme in a slow flat fading channel, it has to be averaged over the probability of error of the particular modulation technique in additive white Gaussian noise channel. What does it mean? That we have a modulator which is our particular modulation scheme, and then there is a path loss followed by noise source, and you give it to the demodulator. Right? So, this is the basic model, and the averaging is done over additive white Gaussian noise channel. So, let us look at the probability of digital modulation in slow flat fading channels. The probability of error in AWGN or additive white Gaussian noise channel is viewed as a conditional error probability, where the condition is on alpha is fixed. The AWGN channel is the simplest practical case of a mobile radio channel. So, please note there are two kinds of impairments that are coming into the picture. One is the additive white Gaussian noise channel and the other is the fading effect. In this model, the received signal is the sum of the transmitted signal and the Gaussian noise. Okay. So, let us talk about the probability of error in this slide. So, the probability of error in a slow flat fading channel can be obtained by averaging the error in AWGN channels over the fading probability density, which is denoted by the PDF. What is the probability of error in a slow flat fading channel? It can be evaluated simply by this equation PE equal to integration 0 to infinity PEx Px dx. So, we have to average this PEx. What is x? X is alpha squared EB over n naught. What is alpha? Alpha is this multiplicative factor which you get when you have the RT received signal equal to alpha t e raised to j theta t st plus nt being the noise. So, P subscript Ex is the probability of error for an arbitrary modulation scheme in additive white Gaussian noise channel, whereas Px is the probability density function of x due to fading channel. Please note x has already been defined as alpha squared EB over n naught. EB denotes the energy per bit and n naught is a measure of the noise power. Okay. Let us look at this slide where we talk about the various probability of errors for the different modulation schemes in additive wide Gaussian noise channel. So, let us now decouple the two effects. So, let us list here the probability of error for some modulation schemes only in additive wide Gaussian noise channel. So, all this we have seen before and have been put here for the sake of comparison. So, either you talk about coherent or you talk about non-coherent modulation techniques. In all these expressions, we have a common platform for comparison, which is EB, energy per bit. Now, please note that we have for BPSK equal to Q function under root 2 EB over N naught, whereas for FSK there is a 3 dB difference Q under root 2 EB under root EB over N naught instead of 2 EB over N naught. These are the coherent techniques. Similarly, for DPSK and NCFSK, non-coherent FSK, it is given by these expressions. What is important here is to note that with respect to EB over N naught, which is a measure of SNR or signal to noise ratio, the fall off of probability of error is exponential. It is e raised to power minus SNR. So, it really falls down very fast. So, it makes sense that if I am working only in additive white Gaussian noise channels, I would rather invest some resources in increasing the signal to noise ratio, and I get orders of magnitude improvement in my probability of error, bit error rate. Right? So, it makes sense here. What we are trying to show here is that it makes sense only in additive wide Gaussian noise channels, but this logic may not hold for fading channels, which is typical of mobile communications. Okay. So, we will refer back to this slide in terms of the exponential fall off of bit error rates of common modulation techniques in pure additive wide Gaussian noise channels. Okay, let us now talk about the probability density function PDF of X in a Rayleigh fading channel. Now, just to recap, the Rayleigh probability density function is given by PR equal to R over sigma squared E raised to power minus R squared over 2 sigma squared. Please note R is greater than or equal to 0. When the input signal at a receiver is Rayleigh, then if you define X is equal to signal power over noise power, and what does that mean? A squared R squared over 2 Pn, Pn is the noise power. The aim is to find P of X. Please remember what we are trying to do. We have a Rayleigh fading environment, right? And we have defined X is equal to signal power over noise power as follows in a Rayleigh fading environment, and we have to find P of X. Once we have that, we can go over and derive the probability of error expression. So, let us see. Let alpha be a complex Gaussian random variable. So, let us denote alpha is equal to x plus yi, and let us say the absolute value of alpha is equal to r. Let us say sigma is a standard deviation, because we are talking about Gaussian random variables. So, if you want to plot on this axis the real alpha and on this axis the imaginary part of alpha, the complex samples of a non line of sight fading signal does look like something like this. All right. The average signal to noise ratio for the channel gamma. So, let us denote the average SNR by this capital gamma is the mean of X, and let us say gamma is equal to A squared expected value of r squared over 2 Pn noise power, which is nothing but a squared sigma squared over Pn. This is coming from the distribution, the Rayleigh distribution. So, this gamma is nothing but the average SNR for the channel. So, our expressions, the bit error rate expressions must be functions of this gamma in a Rayleigh fading environment. Now, to find the distribution of x given the distribution of r, we use the following identity: P of x is equal to P of r dr over dx. This is well known. Here, this is nothing but r over sigma squared e raised to minus r over 2 sigma squared for the Rayleigh distribution, Pn over a squared r. Right. This is dr over dx coming from the previous expression here. Now, gamma is nothing but a squared sigma squared over Pn is the average value of the SNR. So, we get the final result for the probability density function of x as P of x equal to 1 over gamma e raised to minus x over gamma, where x is greater than or equal to 0. Right. So, we have been able to obtain the PDF of x as a function of gamma, which is nothing but the average value of the SNR. Now, we can use this to calculate the probability of error for different kinds of modulation techniques. So, performance of digital modulation in slow flat fading channels. Let us talk about coherent BPSK. So, the probability of error for coherent BPSK in additive white Gaussian noise channel is given by using this expression, and probability of error for PSK is Q under root 2 EB over N naught, we have seen, is given by this expression. Substituting the two equations above in the following equation, what is the following equation? Probability of error x over the times PDF dx 0 to infinity will give you the probability of error. So, I have averaged the probability of error expression, right, over the AWGN channel, and if you do that, PEX can be put as 1 over gamma e raised to minus x over gamma coming exactly from here, and this P of x, which pertains to the coherent BPSK, comes from Q under root 2 EB over N naught is Q under root 2 x, comes out here dx. In fact, this gives you a standard method to evaluate the probability of error, bit error, for all the different kinds of modulation schemes. You just have to substitute P of x properly. So, here we have done it for the BPSK. If you evaluate this expression, you get PE for BPSK as half 1 minus under root gamma over 1 plus gamma. This is the solution for coherent binary PSK. Please note, what is gamma? Gamma is EB over N naught alpha bar squared. Right. So, this is for a fading channel the performance of coherent BPSK. This is different. This is very different from this Q function under root 2 EB over N naught kind of thing. This is an exponential fall off. This is nothing even close to exponential fall off. In fact, it is an inverse relation only. This is a disturbing fact because it tells us that the probability of error in fading channels really does not fall off exponentially with increasing SNR, here average SNR. That means we have to work much harder, we have to increase the SNR much higher to obtain the same level of drop in bit error rates. Let us look at the probability of error for other modulation techniques in fading channels. Relay fading is what we have assumed, and additive white Gaussian noise is present. Now, for coherent BPSK, we have obtained this expression half 1 minus under root gamma over 1 plus gamma. Let us see how it compares with coherent binary FSK, where we have probability of error for FSK is half 1 minus under root 2 gamma over 2 plus gamma, slightly different as a 2 in the denominator here. For DPSK, it is very clear, it is 1 over 2 1 plus gamma, so it is clearly an inverse relationship with respect to gamma. For non-coherent FSK, it comes out to be 1 over 2 plus gamma. For GMSK, the modulation technique that we use for mobile communication GSM standard, it is half 1 minus under root delta gamma over delta gamma plus 1, where delta has these two values for different bandwidth time products. We have talked about this BT product for GMSK earlier. It tells you how sharp or how narrow is the Gaussian pulse used to pulse shape the MSK signal. What is important to note is that in all of these cases, the probability of error falls off inversely with respect to the signal to noise ratio. This is the story for all of them. So, performance of digital modulation in slow flat fading channels. For large values of signal to noise ratio, the error probability of equations may be simplified. See, in most of the denominators we saw earlier, there is 1 plus gamma or 2 plus gamma kind of expressions. So, consider the case of binary PSK coherent, which was half 1 minus under root gamma over 1 plus gamma. For large values of gamma, that is signal to noise ratio, you can approximate it to obtain 1 over 4 gamma for coherent PSK, which clearly tells you that the probability of error drops off inversely. How good or bad is this assumption? So, for again coherent BPSK, where the exact expression is half 1 minus under root gamma over 1 plus gamma, and the approximate expression is 1 over 4 gamma, we have plotted in red the actual value, the exact expression, and dotted blue is the approximate expression, and there is a clear match for high SNRs, and it starts deviating at low SNRs, but fairly a good match. So, for all practical purposes, we can use the practical approximate value. This is the result for BPSK. It does not stop us from approximating all other digital modulation techniques that we have seen so far. So, let us say for large values of signal to noise ratio, the error probability equations can be simplified as follows. For BPSK, we have carefully seen it comes out to be 1 over 4 gamma. For FSK, it is 1 over 2 gamma, right. So, there is a 3 dB kind of effect here. Then DPSK, again 1 over 2 gamma. So, again you can see that in fading channels, the binary FSK and DPSK perform almost equally well in high SNR scenarios. Then non-coherent FSK falls off as 1 over gamma, so it worsens by a factor of 2, and then for GMSK it is 1 over 4 delta gamma, where delta we have earlier seen it is 0.68 for bandwidth time product of 0.25 and 0.85 for the BT product, very large. So, what we learned from this slide is that we have parallel expressions, approximate equations for the bit error probability for the different common modulation techniques while we perform in fading channels. So, let us look at it graphically. In this slide, we want to know the bit error rate performance of binary modulation schemes in Rayleigh flat fading channels. As you can see, there are two categories of curves here. One, the gradually falling curves. On the x axis, we have plotted the EB over N naught, the energy per bit over noise power, which is an indication of the signal to noise ratio. So, x axis marks the signal to noise ratio in dB. The y axis marks the probability of error. Please note, here it is a log scale also. So, x axis is also logarithmic dB, y axis is also logarithmic. Here it is always almost a linear, inverse linear fall off. The first curve is FSK non-coherent, then is the DPSK, and then is the PSK. Here is a typical binary modulation performance in a pure additive white Gaussian noise channel in the absence of fading environment. A simple additive white Gaussian noise channel, it really falls off exponentially. There is a lot of gap, right, and this gap increases at high SNRs. So, as expected for fading channels, the bit error rate has simply an inverse relation with the average SNR gamma. For additive white Gaussian noise channel, the BER falls exponentially. Now, suppose we want to compare, let us say for a particular application the desired bit error rate is 10 raised to the power minus 4. Okay, it is not a very demanding environment. I am expecting a bit error rate of 10 raised to the power minus 4. If I am working only in a pure additive white Gaussian noise channel without any fading, then I require a mere 8 dB EB over N naught to achieve this effect. We are talking about any kind of a binary modulation technique in additive white Gaussian channel. But look at what happens if you move over to the fading environment. Here, even for the best case, you need a humongous 35 dB EB over N naught. That is a lot for a simple requirement of 10 raised to the power minus 4. Clearly, my battery will run out in no time to achieve the same probability of error. But please note, this is the average probability of error we are talking about. We will soon see that the reason why the performance degrades to this extent is because of the presence of deep fades, and when you are doing your average, it shakes the balance. In fact, if you can overcome the effects of these deep fades, then you are back into business. That is, you do not have to work on increasing the signal to noise ratio, you can work around by using some kind of a fading countermeasure. It could be frequency diversity or antenna diversity or polarization diversity or angle diversity or time diversity or code diversity. Any kind of diversity technique which helps you overcome the effects of fading, deep fades, will work very well and will help us get back into shape. Therefore, diversity techniques are very important for design of any communication system which is going to work in mobile scenarios. Okay. It also tells us that by increasing the signal to noise ratio, thereby trying to bring down your bit error rate performance is not the best way to move about in fading environments. Right. In some cases where you do not want to put in fading countermeasures or do not have the luxury to do so, but you have the luxury to increase your signal to noise ratio, normally you put a fade margin, okay, while designing your communication systems. So, you think about what is the maximum fade that will happen. If it is on an average 10 dB or 15 dB, you just add your working value by increase it by 10 to 15 dB. Okay. That is called adding a fade margin. Now, let us move over from frequency flat to frequency selective mobile radio channels. So, let us look at digital modulation in frequency selective mobile channels. The frequency selective fading caused by multipath time delay spread is what we have learned so far. Right? The multipath time delay spread causes intersymbol interference, which results in an irreducible bit error rate floor. The irreducible error floor occurs because of these two reasons. The main or the undelayed signal component is removed through multipath cancellation, and a non-zero value of D, which we define as sigma t over Ts. Right? This is the delay spread, RMS delay spread that we have learnt in earlier lectures, and Ts is the symbol duration. This D causes ISI. The third point is the sampling time of a receiver is shifted as a result of the delay spread. In this slide, let us look at the irreducible bit error rate performance for different modulation schemes in frequency selective fading channel. On the x axis, we have this parameter D equal to sigma t over Ts. This is the RMS delay spread sigma t. Ts is the symbol interval. On the y axis, we have the average irreducible bit error rate. Here we have the different kinds of modulation techniques: BPSK, QPSK, OQPSK, and MSK. Right? And you note that as we increase the D, the irreducible floor, bit error rate floor increases. Now, let us look at another parameter D prime, which is being defined as sigma t, RMS delay spread, over TB, and the bit duration. On the y axis, again we have average irreducible bit error rate. Right? I mean, no matter what you do, you cannot go below this error floor. It is the irreducible bit error rate. Again, we have plotted, and they are fairly close to each other, BPSK, QPSK, OQPSK, and MSK. So, typically what we can learn from the slide is if your value of D prime, which is equal to sigma t over TB, is 0.1, then we are roughly in the range of 10 to the power minus 2, between 10 to the power minus 2 and 10 to the power minus 3 is your irreducible bit error rate. You cannot do any better. But when you plot these curves, the lower two curves belong to the QPSK and OQPSK. So, we can conclude from these that QPSK, offset QPSK, and minimum shift keying are more resistant to delay spread than BPSK, which is at the top of the line. So, some schemes perform better inherently than other schemes. Now, let us talk about pi by 4 DQPSK in fading channels in the presence of interference. We can study the bit error rate performance of pi by 4 DQPSK by using computer simulations. So, in the next couple of slides we can use simulations to study the effects of modulation techniques in fading channels. The bit error rate can be calculated and analyzed as a function of the following parameters. What are these? The Doppler spread normalized to the symbol rate, the delay of the second multipath tau normalized to the symbol duration, the energy to noise ratio, the average carrier to interference power ratio in decibel C2I, and average main path to delayed path power ratio C over D. So, this is the main path and this is the delayed path. So, if you have these parameters, then you can write or make a computer program or buy a computer program which will be able to predict the bit error rate performance in fading channels. So, one of the programs is the bit error rate simulator or BERSIM. Here you have a data source and it could be real data from a TV camera, optical scanner or a computer terminal, passes through a modem. Then we have the fading channel. You can have different models for the fading channel. Then at the receiver there is a modem and then there is a data sink. You can have an alternate way data source, digital hardware simulator, which you can have a PC to do real time bit error rate control, and then a data sink. So, this is a general model for the bit error rate simulator. You can change the type of data, the data rate, the signal to noise ratio, the fading effects, whether it is a frequency flat or a frequency selective fading, right, change the signal to noise ratio and get the different kinds of performance. In this slide we have the bit error rate performance of pi by 4 DQPSK versus C2N. On the x axis we have the C to N ratio, carrier to noise. So, here we have the various curves for different carrier to interference. Here C2I is 20 dB, 30 dB, 40, 50 and infinity, right. And here you have the bit error rate. It is just telling you the power of 10. So, 10 to the power minus 1, 10 to the power minus 2 and so on and so forth. This is 10 to the power minus 5. Clearly, when you have higher C to I ratio, as you move down, your error rate goes down. For C to I greater than 20 dB, the errors are primarily due to fading. But when C to I drops below 20 dB, the interference affects the link performance. Now, again we are talking about bit error rate performance of the pi by 4 DQPSK versus signal to noise ratio. On the x axis we have EB over N naught SNR. On the y axis we have bit error rate going from 10 to the power minus 1 down up to 10 to the power minus 6. But the different curves are for different vehicular speeds starting from 10 kilometers per hour up to 150 kilometer per hour. We are after all working in a mobile situation. So, let us see how it affects our performance. So, as we go up, we are increasing the vehicle speed. We can see that when the velocity increases, the irreducible bit error rate floor also increases. Cannot do better than that. So, inherently, just by being mobile and just by moving fast, you have an irreducible bit error rate. These problems do not exist in your simple additive white Gaussian noise channels. So, fading environment, right, is very different than what we have learned so far, and we have to come up with ways and means to overcome this effect. Please note, if I am on the topmost curve, right, at 150 kilometers per hour, right, for a wide range of EB over N naught, I have bit error rate minus 10 raised to minus 3. No matter how much I increase the signal to noise ratio, see the x axis is SNR, I saturate. This is an irreducible bit error rate. Fine. The knee occurs later point as we slow down. In this slide, we have the bit error rate performance of pi by 4 dQPSK versus this normalized tau over t. So, on the x axis we have tau over t, and y axis is again the bit error rate. Here they have different speeds. This is 120 km per hour for a different kind of C to D ratio, which is 0 dB. We improve the C to D ratio. C is the direct path, D is the delayed path. If you improve that, your bit error rate goes down, speed is the same, and for the same C to D ratio, if you lower your speed, your bit error rate goes down also. All these are simulation results. So, we are trying to say that if you have a good simulator, you can carry out a lot of analysis simply by simulations. Fine. So, in this diagram, we have two parameters, the C to D ratio and the speed of the vehicle. The delay and amplitude of the second ray have strong impact on the average. This is what we take home from this slide. The delay and amplitude of the second ray have a strong impact on the average. Let us now summarize what we have learnt in today's lecture. We have focused our attention on the performance of digital modulation techniques in slow, flat fading channels. We then looked at the performance of digital modulation techniques in frequency selective mobile channels. So, both flat fading and frequency selective fading channels were analyzed today. We focused our attention on pi by 4 dQPSK in fading channels in the presence of interference, and we used BERSIM to find out simulation results and the performance of pi by 4 dQPSK. And finally, we had couple of graphs showing us examples from the bit error rate simulator. Right? We will conclude our lecture here today. Thank you.